Okay, good afternoon, everybody. We're going to have second lecture by Professor Naoto Nagaosa. Yesterday, he gave a talk about superconducting diode effect. Continuing his second talk today, he will talk about photovoltaic effect in noncentrosymmetric quantum material. Please welcome Professor Nagaosa.
Again, thank you very much. Thank you very much, Ingrid, for this invitation and introduction. So today I would like to talk about the photovoltaic effect in non-centrosymmetric quantum materials. So let me start by mentioning about our collaborators, especially Morimoto-san in Tokyo play a very important and major role. And Kitamura-san joined this project. And in recap, I have two very excellent colleagues. One is Izo Lee, and the other is Xiaoshan Zhang. And Shizuka-san was my research associate, and then now the professor in the Tokyo Institute of Technology. And Dr. Yang was originally the student of Weyl at SMU, and came to my group. And now he's with Ashwin Vishwanas at Harvard University. And we have a long-term collaboration with Professor Guang Hu, the Taiwan National University. And of course, for this project, the collaboration with the experimental group are essential. And Tokura, Iwasa, Kawasaki, and also Ogawa group collaborating with theoretical studies in our group. So these are the collaborators. And then let me start with a very simple story about electric state in solids. So usually the chemists are working on the real space picture, and they are talking about the bond and orbital, etc. But the condensed matter physics, usually we start with the band picture and momentum K specify the energy dispersion, right? And in order to connect this real space picture and the momentum space picture, we make a so-called wave packet by making a linear combination of Bloch waves near this momentum. Then both the momentum and the real space could be specified within the certain accuracy, which does not contradict with the uncertainty relationship. Okay. So actually, if we make a wave packet, we are led to the concept of Velic curvature and Velic connection. So to start with the Bloch wave function given by this expression, namely the exponential factor and the periodic part of a Bloch wave function U and K. And then if you are looking at the relationship between the neighboring Bloch wave function at K and K plus delta K, and then you end up with some phase factor, which is exponential to some vector potential A times del K. Sorry, I missed the del K in this exponent. Right? So actually, this is mathematically called a connection in the momentum space, namely the relationship between the wave function at K and the K plus delta K, right? So then we have a so-called parallel transport of this wave function in momentum space. So that's the idea behind this Velic connection. And then once we have momentum and real space position together, they are related to each other by the canonical conjugate relationship. Namely, X real space position is given by the derivative of with respect to K. But if you define this derivative on the curved space-time, and then instead of this usual derivative, we need some connection. Namely, this covariant derivative, and this AN acts as some correction to the real space position of the wave packet X. And then these are physical meaning that you have this shift of wave packet measured from, let's say, the center of a unit cell. And then this shift depends on each band, AM, right? So that AM is called the intra-cell coordinates. So these are related to the real space position. But once you have this covariant derivative, then this operator X and Y are not commuting with each other. And this commutator becomes flux, so-called very curvature in the momentum space. And this non-commutative relationship leads to the additional terms to the velocity. Namely, if you take x dot, right? X dot, and then this x dot is nothing but the commutator between x and h, and then x contains the kinetic energy term and also the potential term. And this commutator with the potential term gives rise to some extra so-called anomalous velocity, which is BMK times del V del Y. So this is usually the transfers to the direction of this X, right? So then the force is along the Y direction, and the velocity is along the X direction. So that's why this naturally leads to the Hall effect. And now we realize that this contribution plays a very important role in the physics of anomalous Hall effect in ferromagnetic materials. So as for this BK, namely the momentum space very curvature, we have a constraint coming from the time reverse symmetry and the inversion symmetry. So the time reverse symmetry connects the BK to the B minus K, and also the inversion symmetry relates the BK and the B minus K. So if we put together, namely both symmetry are intact, then BK is automatically 0. And that means that once you break the inversion symmetry or time reversal symmetry, then this BK becomes finite, and then the geometric nature of the block wave function becomes relevant to the physical properties of non-centrosymmetric or magnetic systems. So these are the introduction to the very connection and very culture. So now, yeah, so the idea is that this is relevant to the physics of a low energy. Namely, the wave function is confined within each band, right? So that's why this wave function attached to this surface. So this surface means manifold corresponding to the each band. So then I believe that this very connection or very curvature are relevant only for the low energy process where the interband transition are forbidden with a high energy excitation. But it turned out that it is not the case. That is a story I want to tell you today. So namely here we have experimental report about the photovoltaic effect. So these are ferroelectric materials, right? And then you have spontaneous polarization. And then this polarization is reversed by reversing the direction of the electric field. So this is a PE curve of this ferroelectric materials, right? And then if you reverse, if you shine light, then you have photocurrent generated without any bias voltage, right? Just a shine light. Then you produce photocurrent, right? And that photocurrent direction is determined by the direction of the spontaneous polarization and the reverse when you reverse the polarization, right? So this was the early experimental observation of photovoltaic effect in ferroelectric materials, right? And then, according to this experiment, there are several theoretical works And you can derive the formula for the second order nonlinear conductivity sigma QRS, and the RS and the Q are component of the current and also the electric field of light. And then you consider the process where omega and minus omega light give rise to the DC current, right? So this DC current depends on the frequency of light, omega and minus omega. So that's why I write this as sigma of function omega. But the generated current is DC current, right? Please note that this omega is not the frequency of the current, but the frequency of the input electric field. Okay, so now this can be derived by the perturbative theory with respect to the electric field, and you have a E dot P perturbation. So that's why you have a P matrix element. And then here is corresponding to the transition from N prime to N double prime. And these are the usual absorption spectrum. But the most important factor is this third one, right? So this phi is a phase of the matrix element between the N prime and N double prime, and its K derivative. And this chi is nothing but the very connection I just introduced as a small a. But here they write the chi, but the similar same quantity. And here is the difference between the N prime and N double prime. So this is so-called shift vector. And this is a change of the intercept coordinates associated with the optical transition from N prime to N double prime. So this formula means that once you have a transition from N prime to N double prime, then you have a shift of a wave function, right? Namely the wave packet. And actually, this chi itself is not a gauge invariant property, because you can choose some arbitrary phase of the Brock wave function. Then that gauge dependence can be cancelled out by the K derivative of this phase of the matrix element. Right? As you can see, this whole combination is a gauge invariant, and these are the physical significance. Right? So that was early history of this photovoltaic effect. In even the 1981. So there's a very original paper by Bartz and Grau. So he basically derived this formula. Right? So that was not the end of this story. So then we came in and explore more physical origin, and it's extension of this shift current idea to various directions. So that is the story of today. Okay, the first things that we try to do is
in the previous page, previously you mentioned that so in the adiabatic approximation, you only consider abelian gauge, but we know that is there any, but generally it is non-abelian matrix form. Then can you some mention about some limitation or some validity of that formulation instead of some small a? Why, if I consider matrix big, so then
actually the reason why this chi appears is that your Hamiltonian is E dot P, right? And P is represented as somehow X, the real space position, right? And the real space position in the Brock basis is given by the K derivative, right? Because X and the K are commutator conjugate with each other. So that's why X is given by the K derivative in the momentum representation. So that is why this K derivative enters into this expression. So this formula does not assume any adiabatic process because we are talking about the optical transition, right? So then it is far from this adiabatic field. So that's why I believe, as far as I believe that this wave connection are totally irrelevant to the high energy optical process. But if you naively pursue the perturbative expansion, then this small a appears in this expression. So that is some surprise. But actually, if you look at the physical meaning of this small a or chi, then this is a shift of wave packet depending on the band, right? And if you switch from n prime to n double prime through the optical transition, then this shift will change. So this change of the shift corresponds to the current. So that is a picture behind this expression.
What is phi?
Huh?
Phi.
Phi. Okay. Phi is a phase of the matrix element.
Which matrix?
Yeah. Let me see. Yeah, this one.
Oh.
This one. Yeah, more precisely, it is the matrix element of the current operator, interband current operator. And another comment for this formula is that you do not use any intraband matrix element. Usually, the current is given by the interband matrix element of the current. So that corresponds to the group velocity of a band is phi. But here, the expression for the DC current contains no intraband matrix element. Instead, it is all coming from the interband matrix.
It's basically virtual process.
Yeah, virtual process. But because of this delta function factor, so this eventually corresponds to the real process. So this is a very subtle point. But you are correct that this is basically or is essentially the virtual process. So the problem is the virtual process can produce the DC current. So of course we already know that virtual process produces electric polarization, right? The polarization is okay, but the DC current is another story. And usually this virtual transition can never produce a DC current. That was a conventional view. But what I want to convince you is that even this virtual process can produce a DC current. Yeah, I think this is the most surprising.
But the finite this current can occur according to this formula.
Yeah.
This happen for any material, or you need some condition for
actually,
very phase.
Yeah. So because the very phase becomes trivial in the centrosymmetric and also symmetric. Then you at least you need to break the inversion symmetry to have a second order process. Right? But you don't necessarily need the time inversion symmetry. So ferroelectric material is enough to have a finite DC current produced by DC electric field. But this time,
If I repeat this calculation, that degenerate band case.
Yeah.
Degenerate band degeneracy in the presence of band degeneracy.
Yeah.
Each optical transition.
Yeah.
Then
Yeah, if it is a Kramer's doublet, right? Then yeah, usually if you have inversion symmetry breaking in the presence of spin-orbit interaction, you don't have a Kramer's doublet. Right. For generic K point. So that's why this formula in most of the case space, except some high symmetry point, you can define the U1 phase because we don't have a Kramer's doublet for it. But yeah, of course, if you have keep inversion symmetry, then to begin with, you don't have this second order process. So somehow, if we break the inversion symmetry, this U1 phase is, in most cases, well defined because you don't have a chromoscopic. So these are very subtle, but okay. So, but now the first thing that we try to do is to look at the role of relaxation or dissipation on this problem. Yeah, in the previous one, we have a delta function, right? But this delta function is coming from the tiny or infinitesimal energy denominator imaginary part, right? So in the energy denominator, you have a small ideal. So that leads to the delta function, right? But the question is, do we need some relaxation for that process or not? So then we explicitly introduce this relaxation for each band in the Curie formalism, and then derives a similar formula in terms of rocket type construction. And then what we obtain is this factor. So gamma is relaxation, right? And E is electric field. And here is a competition between the E square and the gamma square. So the gamma corresponds to some neutral relaxation. Yeah, so the idea is that once you excite the electrons, and then once you have this stimulated emission only, then you cancel this original shift of wave, right? Because absorption and the emission, so that cancel with each other. But once you introduce some neutral non-radiative relaxation gamma, then this is a neutral. So that's why here is a competition between the stimulated emission and the neutral relaxation. So that's why this gamma over square root of E square plus gamma square appears. So this factor, once you assume that E is gamma is small enough, then this factor becomes unique. So that's why you end up with usual E square factor, which is given by the usual perturbative expansion. But the physics is that we really need deregulation to have a finite DC current. So because
if you apply the previous formula with the delta function,
yeah,
actually your DC current will become zero.
yeah, because through this expression, they never have this gamma, right?
Right.
So then it's a
No relaxation.
no relaxation.
Then no DC current.
Yeah, but actually they assume that E is infinitesimal, but the ratio between the E and the gamma really matters. But that physics is missing in the derivation. So that's why we believe that this formula is more physical, right? And actually explain the experimental results like that. And here is the experimental results for the intensity dependence of photocurrent, right? So this pink line is theoretical fitting, and this dot is experimental data, right? So then this saturation from E square to E linear is our prediction, right? And actually for this ferroelectric semiconductor, so this energy dependence of photocurrent, this is incident light energy, and then this calculation and the experimental results fits rather well. And that's why this semiconductor, this band structure calculation can explain the experimental data almost semi-quantitatively, and also the intensity dependence is well explained by the theory. So everything looks okay, and then that might be the end of the story. But now we want to proceed in many directions. So the one direction is in this diagram. We have so-called Keldysh crossover. So namely the frequency of light and also the field strength. So in this plane, we have some crossover which occurred at around this line, which is called the Keldysh line. So in this way, your frequency is high and electric field is small, right? And then we are talking about the nonlinear optics and photo-induced transition above the gap. But if you go to along this line, so for example, you can apply the DC electric field, which is high enough, then you have a Landau-Zinner breakdown. So then the question is, do we have this non-reciprocal Landau-Zinner breakdown or not? And actually, it turned out that this Landau-Zinner tunneling becomes non-reciprocal, namely the directional dependence according to the shift vector as just introduced, right? So the idea is that this Landau-Zinner formula is coming from the ratio between the this decay length of the wave function inside the gap and also the distance where this electron should tunnel through this gap, right? So this ratio appears in the exponent of this Landau-Zinner transition probability. But actually, once you have a shift of wave packet corresponding to the transition from one to the other band, and then this shift vector has the opposite sign between the left and the right direction. Okay, so that's why this probability for the tunneling, Zinner tunneling, depends on the direction. So the sign E matters because this sometimes this distance becomes shorter compared with the other direction. So this is the same physics as shift current I just described. Yeah, instead of optical transition, so here we have a transition due to the tunneling along this two-tip band structure, right? So then even in this tunneling or Zinner, Landau-Zinner regime, we still have a non-reciprocal tunneling problem. Okay.
But so in the previous two pages before, elementary question, what does it mean? Keldysh line.
Huh? This one?
Yeah, Keldysh line, what does it mean?
Let me see. Yeah, so C is some, let me see. Yeah, C times F is the energy, right? Gained by the electrons when you move with correlation length C. C is determined by the gap. The usual C is 1 over gap, right? Coherence length. And then this C times Fk defines the energy. And this energy could be smaller or larger than the frequency. So that gives you the adiabatic and the non-adiabatic regime between the two. So that is Keldysh crossover. So you can look at this reference for more details. And this phase diagram, or not the phase diagram, this plane is most fundamental for the non-equilibrium quantum systems. Okay, so now there are two types of photocurrent. So the one is just the usual one. So usually the solar cell is composed of p-n junction. So why the p-n junction? Because you have a gradient of a potential for the electrons and holes, and you have optical transition in this p-n junction regime. And then these electrons and the holes are separated by the gradient of this p-n junction, right? So in that sense, you need the external potential to produce a DC current. Okay. But now the shift current is totally different. You don't have any gradient or inhomogeneous structure. Simply you excite the electrons, and because of this shift vector, you have a shift of a wave packet that results in the DC current, right? So no field to accelerate. Then next question is transport of photocarriers are really needed. So namely, we don't need any acceleration of these carriers. Is that the transport current of photocarriers? Or even the photocarriers are needed, even without the photocarriers, can we produce the DC current? So that is a question. So for the second question, I want to raise the question which you already asked, namely this energy denominator, the real part and the imaginary part. And the real part corresponds to the virtual process without any energy absorption. And that corresponds to the wave function is modified and dissipation is. So this second delta function part is a real process respecting the energy conservation and dissipation costs, right? So then the next question is, do we really produce a DC current with this virtual process? So that's the question we asked ourselves. And before going to that, let me explain the shift current under the external bias, right? So we apply the voltage externally, namely the electric field, and then what is the current? So then this current is given by the two components. So the one is the shift current at the zero bias, and the other is due to the acceleration of photo-induced carriers. So that photo-induced carrier is a lifetime tau, and its transport time is also tau. So that's why this second contribution is proportional to tau squared, right? So, and then because the dispersion of electrons and holes are essential for this current, then it is given by the difference between the conduction band and valence band group velocity, right? And also we can talk about the shock noise of this photocurrent. It again due to this transport current and then proportional to tau, the lifetime. And as you can see, once you have almost a flat band, namely the photocarriers are not moving, then you have a flat relationship. So the J does not depend on the external electric field, and the noise is suppressed. So that means for the solar cell and also the photo detector, we don't want this slope, right? So that's why the photo carrier should be rather localized or very low mobility. That is preferable. This is extremely or totally different from the usual design principle of photocurrent in circuits. So these are new types of current may be quite useful for the application. And actually, this experiment shows quite a large temperature dependence of this slope as a function of voltage. But as you can see, this zero bias photocurrent is almost independent of the temperature, right? So this is quite consistent with our previous formula, saying that this first term is tau independent, right? But the second term is strongly tau dependent. So that is quite consistent with this observation, right? So that is
Temperature dependence
is a mobility
comes
changes
from
right?
tau. The temperature dependence comes from tau.
Yeah, tau. So the transport lifetime depends very sensitively on the temperature. So actually, I will be back to this temperature dependence later. And then the question is, do we really need a transport of the photocarriers or not for the shift current? And it turns out it is not needed. And then we are motivated by this experimental paper by Kawasaki group. And this again, this same polar semiconductor. And then this mobility of the sample can be controlled by the sample preparation, right? So from sample A to sample L. So the mobility before the photoexcitation is orders of magnitude different, almost 7 orders of magnitude different. And for example, if you look at this sample L, it is strongly localized. You don't have any transport over carriers, right? And sample A is relatively high mobility, right? But you can change the mobilities quite a lot, right? But if you look at this photo current induced by the radiation, right? So this is a sample A, and this is a sample A. So if you look at this y-axis, right? So this zero bias current is almost the same. This is around 80, and this is around 80 or 90, right? So this mobility of the photocarrier doesn't matter for the photo-induced DC current at zero bias. But if you look at this slope, right? So the slope is quite different. So this x-axis is the quite a different scale. This is a 50, but this is a 2, right? But the slope looks similar, means there is a factor of 25 or 30 difference of this slope. That corresponds to the difference of lifetime or mobility. So this is a plot as a function of that shift conductance representing the mobility of photocarriers, and here is a shift current. So zero bias shift current is almost independent, right? So these are linear scale, but this is a logarithmic scale, right? So these are 8 or even large amount of a difference, 8 orders of difference in the mobility or shift conductance does not affect this photocurrent. I find this very surprising, right? So the localization does not matter for this shift current. So this is the experimental message. And actually, we tried to model this problem in terms of the one-dimensional tide binding model. And then we introduced site energy alternation, which is a VS, and bond alternation. So together with this small data and the VS, we can make a system ferroelectric invariant symmetric gradient. And on top of that, we introduced some disorder potential VI, which will localize the electric states rather easily because we are thinking about the one-dimensional system. So the localization is very strong, right? Okay, then we measure the localization length from the inverse participation ratio. Oh, be careful. Okay. Oh, sorry about that. No problem. So then once you have this disorder potential of the order of 0.5 or 0.5 yellow, right? Then this inverse participation ratio is already 0.01, 0.1, etc. So this means the localization range is typically 3 or 4 sites. Okay?
What is inverse participation?
Yeah, given by this. Given by this. So then if you have only one site localizing, then it is 1. But if it is localizing n sites, so then it is 1 over n squared. So then
small means more localized.
Yeah. Small, large means more localized. Right. So once you have a extended state, then this is 1 over n squared. So then it becomes small. So small means extended, and large means localized. And yeah, the localization range is typically given by this. So once it is 0.1, so this is typically the 3 in that times large constant. Right? So then once we have a very strong localization, then what happens to the photocurrent, right? And then up to 0.5, our photocurrent is almost unchanged, even though the localization length is much shorter than the sample size. Right? So this means the shift current is so robust against the localization, and we don't need any transport current of photocarriers. Right? But if you further increase this, and then you mix up this valence and conduction band by the strong disorder, and eventually this character of polar system becomes negligible, and then it goes down. But clearly, we can control the localization within each band, and also the gap size, right? So gap can be controlled by the parameter, and the disorder strength can control the localization. So this is a very good model for us to study the two aspects. So one is a mixture of a valence band and conduction band, and the other is a localization for each band.
Then what's the physics of it? In order to have shift current, eventually electron should move, right?
Yeah, electron just shifts.
Shift means
Not,
moving. You don't move electron.
Yeah, actually it moves on the atomic scale, but not over the sample. So the electron moves at every side.
It's jumping.
Yeah, but
Localize the electron.
yeah, it's
jumping.
a shift. Yeah, once you have a shift of a whole electron, then it will result in the DC current. But this each electron do not have to move from one to the other end.
So electron is shifting by through virtual process.
Yeah.
The virtual process. So
Yeah, but at this stage, we still excite the particle.
Yeah.
This energy is consistent with interval transition. Then the next question is once we lower the energy and below the energy gap, still can we produce photocurrent? That is the next question.
as far as you allow virtual process, then there should be finite shift current.
Yeah, exactly. But that is what I want to talk about. Okay. So now on, right? So okay, so then the next question is, do we have a real DC current with a Barger excitation? But the Barger excitation corresponds to several possibilities. So the one is so-called exciton. Exciton has no free carriers, so it's a neutral particle, right? Electron hole bound state, right? So then exciton can have polarization, but not DC current, right? But also we can excite the low energy collective mode, such as so-called electromagnon in multi-ferroelectric materials, right? So this is a combined nature of polarization and magnetization fluctuation. So then we propose in two theory paper whether we can we can support the DC current by the exciton excitation or magnon excitation. So, okay, then the exciton and electron magnon without the electron hole pair can support the DC current or not. So that is the next question. And we did some calculation again in terms of Kurdish formalism. And then the advantage of a QDish is that we can take into account this diagram, because the QDish is compatible with the Feynman diagram technique. And actually, yeah, Hanai-san was working on this, right, with Rito, right? And we learned a lot from his paper. And then basically we can solve the base circuit equation for the exciton formation. And correspondingly, once we have a Green's function in the QD space, then we can talk about shift current in terms of this Green's function. And then this is a final formula. And then this shift vector appears, but this shift vector should be a weighted average over the momentum component K, which constitutes the excitonic state. So this K integral corresponds to the bound state. So the exciton contains many K components because it is a bound state, right? But the basic information is that exciton extension can result in the DC photocurrent, right? And also, this Stephen Lewis group did a very extensive calculation for the German sulfur concerning the calculation of the exciton shift current, which was published 2 years ago. And experimentally, we and the experimental group collaborate on this cadmium sulfide.
In the previous page, how, I don't understand.
Yeah.
How exciton obtains electric polarization? What is the setting?
Oh, okay. So actually, we assume some noncentrosymmetric band structure, and then that appears in this shift vector. Because here we have A2 and A1, which is coming from the inversion symmetric breaking.
How can I know that the shift current mostly appears from exciton polarization or electronic shift current? How can you distinguish that?
Yeah, because of the excitation energy. Because we can control this, right? Incident light energy. And below the particle Hall continuum, we can excite the exciton. Then the question is compare this linear absorption spectrum and the excitation spectrum of photocurrent. Then you can compare this energy. So then, yeah, that is exactly what we did, right? So this is a linear absorption spectrum. So you have exciton peak, and here you have a shift current, right? Due to the particle continuum. And this is still a very tiny signal, but we have some shoulder correspond to the exciton absorption. And this is a photoconductivity tensor for the second order. And yeah, you can see it's a peak. So we believe this is due to the some exciton induced shift current. And another example, yeah, this is still unpublished data by Kawasaki group, right? And then this is a copper iodide. So the advantage of this material is that this exciton peak is very well defined compared with just a shoulder, right? And then this G12 corresponds to this interband transition and its exciton state, and the G3 is a higher energy exciton. And then corresponding to this exciton peak, you have a clear exciton peak corresponding with photocurrent generation. So this is definitely the shift current due to the excitonic states. So you don't need a free carriers, just the particle Hall combined. Bound state can produce DC current. So that is a message from this experimental.
So when you calculate this exciton contribution,
yeah,
you need exciton band structure.
Yeah.
So then you're claiming the Berry space of this exciton band should be different than original.
Actually, we are looking at the gamma point of exciton. So the center of mass motion is always 0 because the light wave number is very small compared with brilliant oxide. So we assume the wave number of light is 0. So then you expect only the gamma point exciton. But this gamma point exciton is given by the linear combination of particle and whole, right? This so-called how to say relative wave function between the electron and hole. So then it is a weighted average of.
So my question is, I understood from the beginning.
Yeah.
The mathematical origin for this shift current is the difference of Berry phase or Berry curvature.
Yeah.
So then, in the case of exciton, you excited your conduction electron to the exciton band. Then there should be the difference of Berry curvature.
Exactly. But the origin is coming from the difference of Berry connection between the valence and the conduction bands. Right. So
And now,
yeah, the idea is that right. So you have to start with.
Yeah.
You have this, and then you have a transition, right?
yes,
In momentum space.
Yeah.
But the exciton is a bound state. So you have a linear combination of all these transition, right?
Oh.
And then create the exciton.
I see.
And then it is right. It will put together,
Oh, I see.
right? These are
So
different in the
all effect of
yeah.
Berry curvature
Yeah,
is
exactly.
not into
Yeah. Sorry, not the very curvature, very connection.
connection.
So then actually one of my friends in Taiwan did a very extensive calculation and eventually succeeded to produce this spectrum. But it's a huge calculation. But in any case, the essence is that this particle hole bound state can produce DC current. But even more surprising is phonon-induced, right? So this is a typical ferroelectric material, barium titanium, right? This has been already published. And barium titanium oxide is the most representative ferroelectric materials at the transition temperature near 400. And then below that, you produce spontaneous polarization. And then here is a linear spectrum, and you have a particle Hall excitation, and you have a phonon excitation in the terahertz region. So there are orders of magnitude difference in energy. And without this particle Hall continuum excitation, you don't have any photocarriers. You just excite this phonon spectrum with a terahertz pulse, right? Which energy is at most extend towards 10 milli. While the band gap is 3 or 4 electron volt, right? So then the question is, what happens if we excite these phonons? And this is a spectrum, not the spectrum, time evolution of photocurrent, and this integral over the time remains finite. That means the DC component actually survives. And then the direction of the photocurrent is reversed once you reverse spontaneous polarization. And more interestingly, if we apply the bias voltage, then it's a totally independent, right? So this means you don't have any photocarriers, right, to be accelerated. So this suggests or indicates that the photocurrent without the photo-induced carriers are finite for these ferroelectric materials, right? So then theoretically, we can talk about this process in this Feynman diagram, and we the essential point is that the light cannot induce the real transition of a particle Hall. This is a virtual transition and coupled to the phonon propagator. And the phonon is really excited. So the energy is absorbed by the phonon, right? But not by the virtual particle Hall excitation of electrons. So then this diagram can result in the DC current. But as you are interested in the linear response, of course, you don't have this line. Then this is the usual RPA type diagram, and you never obtain the DC current in the linear response. But if you go to the nonlinear second order response, then this additional vertex will help you to induce DC current. And another important message here is that all this matrix element is an interval matrix, not the interval. So then this usual transport current is missing here, and you don't have any bias voltage dependence of.
When you calculate the previous diagram.
Yeah.
If
Yes.
there is no phonon.
Yeah.
Then you don't have this diagram.
Yeah. So what happens
My
is
question
you
what's the role of phonon?
okay. Phonon is absorbing the energy.
Yeah.
To support the DC current, you always need a constant input of the energy.
Ah.
So the absorption is always needed. But
But absorption itself doesn't create or contribute to the current. But if I just delete the phonon,
Yeah.
you cannot draw this diagram.
yeah, you don't have any. Yeah, suppose you have a couple, direct coupling to the phonon.
Yeah.
Yeah, if you don't have this particle Hall bubble, nothing happens. Just you excite the phonon. But you have a virtual excitation of this one. So that results in the DC current.
Let me translate
Yeah.
Yungbang's question in my way. So if I integrate out all electronic degree of freedom,
Yeah.
then I obtain effective action for phonon.
Mm.
Then can I interpret that in your previous shift current mechanism?
Yeah.
So what I mean is
Mm.
you have some phonon interband transition and
Yeah.
phonon berry connection.
Yeah.
May I interpret
Yeah,
that
yeah,
in
yeah,
that
yeah,
way?
yeah. So actually, you can regard this part as an effective coupling to the electromagnetic field of phonons. And also, this is a nonlinear coupling to the electromagnetic field. So then you can formulate this problem in terms of the phonon theory. But the origin is always electronic, right? Yeah, if you just have nuclear ions, right, then you can never produce the DC current. Yeah, that's also true. So eventually, you need to turn your charge or current into the leads, right? Yeah. Then you really need the electrons. It's not the nuclear. So, yeah, this is a very subtle point, but always we need an electron hole virtual transition. So the electron hole virtual transition is nothing but electric polarization, not the current, right? But due to this absorption of phonon, it will be the real DC current. Yeah, I think this is a highly non-trivial, and people never consider this possibility. Up to now. So the insulator is not that insulated. So that is our message. Okay, so we can do some model calculation for again for the one-dimensional alternating problem. And then my colleagues in Taiwan National University did a very extensive calculation, electronic states and the phonon states and the electron-phonon interaction. So this is again the huge calculation, and he ended up with nonlinear optical conductivity. And this one is almost comparable to the particle excitation and the phonon excitation. Right. And then experimentally, this glass coefficient, analogous to this nonlinear conductivity, is also similar, right? And slightly larger in this terahertz region. So that's why we believe that, yeah, this serious calculation also support the phono-induced DC shift current is real. Okay, I think I have enough time, but I think I can skip this part. And summary is that I believe now the nonlinear responses is quite relevant to the quantum geometric properties, and very connection, very curvature, and even the Riemannian geometry will appear in this nonlinear response, and especially the shift current, nonlinear optical process in non-centrosymmetric materials as a geometric current, finally, even in insulator, Anderson insulator and the excitons and the phonons, right? And then the virtual excitation can produce a DC current. I think this is a very new concept in condensed matter physics, and probably will have a large impact in the future. So we have a virtual process and a real process, but the virtual process can turn into the real DC current. So that is basically the message I have, and I want to reply any questions. Thank you very much for your attention.
Can you explain the first part?
Yeah.
Quantum geometry.
Actually, Junior and myself and even Ashmi were thinking about the formulation of nonlinear optical conductivity in terms of Riemannian geometry. And the idea is that this metric tensor and the connection correspond to the Christopher symbol, and Riemannian curvature appears in the linear and the second order and the third order linear optical conductivity. But not the generic one, but you need to specify the combination of the omega. You have several omegas, right, appearing in the nonlinear activity. And let me see. Yeah, so here is some formula. And the basic idea is that this matrix element of real space coordinates R is given by the derivative with respect to K. Right? So this is the origin of some connection in the momentum space. Okay, and then you can define the base of a tangential space, right? So then this is so-called moving plane, and then the inner product corresponds to the quantum metric, and the derivative of this basis corresponds to the connection, right? And this connection is nothing but a Christopher symbol in Riemannian geometry. And if you take a covariant derivative of this basis, then you end up with a so-called curvature. And this Riemannian curvature is defined in this way. So, and then this first order linear response is nothing but this metric tensor, and this second order process. And the injection current is given by, again, the metric tensor. But this shift current is given by this Christopher symbol. And but here you assume the omega and minus omega goes to 0 shift current, right? In injection current also omega and minus omega. This omega is similarly, we consider the omega and minus omega and the 0 response. So that is third order injection current. So that result in this Riemannian curvature term. And then you need to specify the combination of the omega in the proper way. Only in that case you can relate this nonlinear optical conductivity to some Riemannian geometric quantity. For generic omega 1, omega 2, omega 3, etc., then you cannot do that. So you need to choose some good combination of omega. So that is a story.
Okay, any question from Zoom audience? It's no question.
Can I consider some diffeomorphism property? Diffeomorphism property. Can you, I think, change the diffeomorphism here? Change of metric tensor, I mean, change of plane. Coordinate.
Yeah.
So in this case, many things are not invariant. I mean, previous shift current is gauge invariant.
Yeah.
In this case,
oh, okay, probably, yeah. Actually, in the general relativity, Christopher symbol is not gauge independent quantity, right?
Yeah.
But we do not need such how to say gravitational invariance, right? Yeah, this one is gauge invariant as far as we are gauge degree of freedom is concerned, but not the general invariance with respect to the coordinate change. Yeah, these are different from general relativity in that sense.
Okay, any more question from Zoom audience? If there is no more question, then we will close this lecture. So as announced, he will give his third lecture tomorrow, same time, starting 2 o'clock. Okay.
Thank you very much.